Any questions for homework stuff? No questions from homework stuff? Yeah? If you remember, we have a quiz on Tuesday. You guys remember? Alright, so just to remind you guys, quiz Tuesday, 4-7, 4-9, 5-1. Remember, it doesn't include the summation of I squared stuff yet. Like I said at the end of class last time, it goes from the optimization problems to antiderivatives to finding the area using 6 rectangles, that kind of thing. Right, left endpoints, right endpoints. So that's what's going to be on the quiz Tuesday. Okay, all right. So there's no questions. I'll get right back where I was. Say again?
Ask you about 24 and 5.
Yeah.
It's just generally, is there a certain system that you're looking to do within these bubbles? Because it seems like a lot of times the factoring that you have to do with the eyes.
So let's take a look at 24. Let's get that set up maybe. This is section 5.2, 24. It says use the definition in Theorem 4, which is that Riemann Sums stuff. There it is. By the way, I don't think I used Steve's name yet. Riemann Sums is when you estimate area by using rectangles. There's also other, if you take Calc 2, you also learn trapezoid rule. So you actually estimate not using rectangles but using trapezoids, because trapezoids would actually fit better. Instead of just a rectangle, use a trapezoid. So one side of it could be curved, and that would fit better. Does that make any sense at all? And it's actually easier than it seems, because you have to worry about, well, what's the slope of that one side? But it's actually not that horrible, and it fits better, and it makes an immediate improvement to the estimation. But what we use is called Riemann Sums. It involves estimating area using rectangles. So that's what they want here, and this is this thing that you got to know. If you can't break this down, not just for yourself, but listen to me when I break it down for you, what does this piece represent? What about the rectangle? The area of the rectangle. This is the height, the width. So these are the areas of rectangles. This just says add up all the areas. Oh, okay. That makes sense. Right? Add up all the areas. And this is where I just allow what to happen. Sure, what's that mean physically? Yeah, every rectangle is getting infinitesimally small because I'm going to use an infinite number of rectangles. I'm going to shove an infinite number of rectangles in this little space. Which is what calculus allows us to do. Right? How many pounds can you put in this car? Well, let me take a limit. Now just to remind you guys, while I've got this up here, the symbol we use for this is, remember this? Elongated S is this infinite sum. Because we don't, math people, we don't like writing this much. We're like, let's shorthand that. So if I let it go to infinity, these get infinitesimally small, and then it doesn't matter what x I use. What x I use? In fact, think about it. What x's will be used? if I put an infinite number of rectangles in here, what x's would I not use? I really want you to think about it. Because normally if I use a big ass rectangle, I'm not using any of these interior x's at all, am I? I would only use x0, x1. If I use an infinite number of rectangles, am I not going to use every freaking x in there? Because every x is going to have its own little rectangle in the limit. So this is every x from A to B. They all get used. So why would I call them xi when there's not a countable number of them? There's an infinite number of them. I'm just going to say x. So this going from here to here is so beautiful. It's just, it's just math people being lazy. That's too much shit to write. Let's write like this. Or frugal with her time. Okay, so how do I start to set this sucker up? What do I need to figure out first? Delta x. Delta x, because that leads me into a way to figure out every step, the xi's. Right? So what's delta x going to be here?
It's going to be 2 minus 0 over n.
Beautiful. Beautiful. So that's just 2 over n. It's always nice when you have 0 as one of the endpoints. Always nice, but you won't always have that, so don't get overly excited. Now what's xi? In general, it's a plus I delta x. A is 0, and delta x is 2 over n. So I get xi is 2I over n. I mean, right, this is not horrific. Because in general, how do I get from one side of a rectangle to the next? I add a width. So all this is saying is I'm going to add this many widths. And I'm going to start here. You can read it in English. All right, and see how I get this, which gives me a way to write this, and what do I do with this? Plug it into this. Yeah. So what's f of xi would be twice 2I over n, so 4I over n, minus cubed. So it's build, build, build. Delta x gets you started. It builds what the xi's are. Throw that into the f. Throw all this shit into here. This is what you worry about at the end. Or towards the end. The big thing people forget is you feel like you've done so much work already, but when you put it in here, it's got to be that times that. The delta x. Right? So that's what it says. So it would be the limit of the sum of 4I over n minus 2I over n cubed times 2 over n. Yeah. You guys okay with, I mean, as long as you write this once, I'm okay with you simplifying it like that. It's fine. Is that enough for that, or, I mean, obviously, the real work comes next, but if you can't even get it set up, you can't even.
The question I had was, is it better to unite all of those into one term?
Oh, no, definitely not. No.
Or just factor individually?
Break the summation up, so you can focus on each power of I. This poor little I is like an afterthought. You want to focus on each power of I, because I have ways to write this. I don't want to ever combine the fractions or something.
Yeah, that's what I was trying to.
So you're going to have a sum with I in it, and you're going to have a sum with I cubed in it, and those are two that we know how to rewrite. The limits make those parts go away. It's so nice. It's sort of like derivatives. Didn't the h always cancel for the stuff we looked at? And that was the problem. So here, the ends are the problem in a way, and the limit makes them go away. All right, clear. Anything else from homework stuff? Okay. Okay. So here's what we did last time. We have this guy here. Let me see if you guys. Let's do this. You have some problems in the homework that are purely geometrical problems. Okay, Jeff. Sure. Let's do one. I like it. So that one there. So if I said, so here's f of t. What is g of 2? Yeah, how do you get that? What?
The graph.
So you get,
The graph.
what about the graph?
The point.
What did you find? What does this ask you to find? What is this? What is this physically? The area. So here I'm assuming like A is 1, is of course where things are starting. So what's g of 2 would be the area from 1 to 2. It's just a freaking rectangle. 1 times 2, so that's 2. So what's g of 3? Take a minute and try to figure it out. Don't say anything. Now again, what does g mean? It means from 1 to what? So to whatever, right? So g of 2 is from here to 2. G of 3 is from here to 3. Well, you already know from here to 2. It's a triangle. Do it. Have you guys done it? I don't see a lot of writing. Are you guys doing it in your head? I like it. It's good if you are. You're just staring at me and waiting for me to tell you what the hell it is. It's bad. So it's going to be 2 plus, how much more area have I picked up? Yeah, half the base times the height. 1/2 1 times 2 is 1. So g of 3 is 3. I like it. So it just happens to be the way I've set it up. It's not always g of x equals x. You figure out the areas. So what is g of 3 minus g of 2? Well, number-wise, that's just it's just 3 minus 2, right? G of 3 is 3, G of 2 is 2, so I get 1. What does this represent physically? The area under F from 2 to 3. Doesn't this represent this area? So what's G of 3 minus G of 2? It's going to be this area here. If I take this minus this, I'm left with this. Very simple physical idea. Very simple. If it isn't, you're making too much out of it. And how do we represent the area from 2 to 3 in symbols? Wouldn't that be this? I don't even need the T's anymore, you just call them X's. Isn't that what that is? Isn't this the area? From 2 to 3, and this is the area from 2 to 3. Are you guys with me? Alright, now. Good, I love it. So there are problems in the homework where they ask you questions in this form, and you just have to use geometry to get the answer, because fundamentally this is a question about area. So if the area is easy, if it's a freaking triangle or something, I'm just going to do that. I don't need calculus, right? But the minute I have something like this, geometry looks at that and says, oh shit. I don't have a freaking clue. And then calculus says, I got you. Now here's how calculus has our back. What did we figure out last time about the derivative of this? Yes. G of x is this integral. What's the derivative? It would be f of
It would be f of x.
f of x. I like it. And again, very quick. I went over this last time. Very quickly. This is the one that involved putting tape on something. I don't know if you guys like that analogy or not. I almost don't care because it's good. Period. I don't care. The whole thing about putting a tape on around a circle and then comparing the circumference to the area, that kicks so much ass. No? So here, if I have a function and I go from a to x, the derivative would be if I take a little step past that. How much area do I add? Well, h is infinitesimally small eventually, or I'm going to let the limit, in fact, what is g prime? It's going to equal limit as h goes to 0 of g of x plus h minus g of x over 8. I guess I'll just do the whole thing again. So what is the height? So this is going to be this extra piece. Do you see how it relates directly to this being this extra piece that I've tacked on at the end? Are you guys seeing the connection? So what is the area of this rectangle? Well, in the limit, the height's going to be f of x. All right, let me make sure you really understand. Is everybody with me that this difference is the area of that rectangle? The same way that this difference is the area of that triangle. Because that's how much area you added on after 2. So this difference is the area of this rectangle. It is f of x tall, and how wide is it? H wide. So if I replace this with f of x times h, I get freaking f of x. This is huge. Some of you guys, I know some of you guys know a little calculus. You know that integrals are antiderivatives. So of course, if I take the derivative of this, I should get back to the function I had before. That's what that says. That's all that says. If I do antiderivative of f, and then I take a derivative of that, shouldn't I get back to frickin' f? It's like if I add 2 to a number and then I subtract 2, what do I get? The number in the first place. I mean, that's just doing the opposite to get back. Okay. I'm going to take that red away, because that's from last time. I need this. Okay. So right here, I've got, let me generalize this, the integral from a to b, f of x dx. I'm just going to generalize what we got here. It would have worked no matter what numbers I put down here. If I did the same thing, it would have worked. No matter what the functions were, it would have worked the exact same way. So the integral from a to b f of x is equal to the area up to b minus the area up to a. That's all it says. Please see that. G is the area function. So if I do the integral, the area up to b minus the area up to a, that's the area between a and b. Which is what this, or what's what this wants. Please. What does this represent? Area from A to B. What does this represent? Area from A to B. And we actually, this is building off of this that we saw physically just a minute ago. But what is, now if G prime is little f, what is G? Big ass F. Be careful now. I'm going to be a little more specific than I was last time. Big ass F. Let's see. Yeah, okay. So FTOC 1. What the shit is that, Jeff? It's not a radio show from New York. It's Fundamental Theorem of Calculus Part 1, which states this. If G is the area function, then G prime is the function itself evaluated at x. That's FTOC 1, right? leads us directly into this fact right here. If I know the derivative, I can then state the antiderivative. So if g prime is f, g has got to be big ass f. Maybe. Everybody remember this?
Yes.
Little f and big ass f? Okay. Because this is so kick-ass. So that means that g of b is f of b plus c. Is that amazing? Is that like holy shit? No. Freaking g of x is f, so g of b is f of b plus c. Minus, what's g of a?
F of A plus C.
Big ass f of a plus c. What happens to the c's?
They cancel out.
Freaking cancel. That's why we don't give a shit about them when they have definite endpoints. They cancel. Okay. I have a feeling that you're not truly understanding the importance of this. Do you like that method we're using? The limit as n goes to infinity, sum I equals 1 to n, f of xi times delta x. You like doing that? Something else, I really love it when you say you do, because I do too. I have a feeling most of us would rather not. So it's sort of like limit definition of derivative. That was so much fun. And then we learned the shortcut. Then we had limit definition of integrals. And now we've got the shortcut, which is just find the freaking antiderivative. So let's do an immediate example, even though we've done one before. We'll do another one now. Just remind us. So watch this shit. So what's that one we just did a minute ago? That one from your problem, 0 to 2, what was it? 2x minus x cubed. So using FTOC 2, which is what this is FTOC 2, right here. This is Fundamental Theorem of Calculus 2. There isn't a part 3. They never got the budget for that. They stopped at part 2. There's no prequel or anything. Using that, if I say use this, what does that tell you? Find the antiderivative, plug the endpoints in. So let me show you the way we do this, just so you know what symbols to use. So I'm right here, okay, 0 to 2, 2x is x cubed. What is the antiderivative of 2x? X squared. Antiderivative of x cubed. It would have come from x to the 4th. But if taking rid of 4 would be here, there's not supposed to be a 4 there, so it's over 4. We don't write the plus c when it's a definite integral. Definite integral meaning it's got a range defined. If you see something without those limits, 0 to 2, if it's just like this, that's just asking you for an antiderivative. That's another way to say what's the antiderivative of this. Then you better put freaking plus c. But what do we know is going to happen every freaking time when I have A and B, I'm going to have the c's cancel. So why write it down? That's why people start to forget to put the plus c, because you don't have to include it on definite integrals. And then here's how I illustrate from 0 to 2. That's the notation we use. So see how this says put the top one in first. Do you see that? I like that. I just realized that. That's my old song. Top first. So you put 2 in. So 2 squared minus 2 to the 4th over 4 minus, and of course when I put a 0 in, I get a big old 0. So I get 4 minus 4. It's a long way to go for that, isn't it? You guys see that? So you get 0. And let's see why that makes sense. What does this look like if I graph this thing? So it's got a 0 and it's got one at, here's 2. It's got one at rad 2. All right, let me see. Yes, kind of. Want to see what this thing looks like when I graph. Quick graph. So it's got an intercept at 0 and an intercept at plus or minus rad 2. And I just care about the rad 2. Right. At 1, it's at 1. I like it. And at 2, it's at -2, -4, it looks like. So it looks like this, sort of. So this area here is positive, right? And remember, the interval is always the area between the function and the x-axis. So past this, the area we're talking about is this area. Now that's skinny and that's fat, but it does look like it makes sense. Maybe that area cancels that area. You see, that's why we got 0. Does that make sense? How do I check this using technology? I put this into y1, and I do calc number 7, the interval 0 to 2. Okay. So when you do that whole thing for the problem you're looking at earlier, it looks like it should come out to be 0. Which I love it when students are like, oh, but to me, I'm like, that kicks ass. Everything died. Awesome. Okay. So just to make sure you guys really get this. This symbol always means now that we've tied them together, this symbol means antiderivative. That's what an integral is. When it has endpoints on it, when it has like 0 to 2, you plug them into the antiderivative. You evaluate them at those endpoints. So if I had a problem like this, is that asking for an area? No, it is not. How can you tell it's not asking for an area? There's no region, there's no endpoints. It's actually asking for the function that I could use to find area. It's sort of the difference between finding a slope at a point versus finding the slope every freaking where. This is finding the area between two things, and this is finding the area wherever the shit. Right? It's the general area formula. So what would this be?
Tangent theta, no?
Almost. It's co, so it's negative. Negative cotangent theta. Plus C. Why is the plus C got to be there? Because how could it cancel when there's not two things subtracting, right? So how would I do this then? Let's do, it's nothing too freaky. So anybody see how you got most of the work already done on this? Should be true. But yeah, most of the work already done. Because how do I integrate some function? I first find that function's antiderivative. And what's the extra step now because it's got these? It wants an area now. Do I write the plus C?
No.
No. I want to go from pi over 4 to pi over 2. So this would be negative cotangent pi over 2 minus negative cotangent pi over 4, and people get tripped up by negatives and stuff. It's this evaluated at this minus this. Okay, that's going to be plus now. Not a big deal. What is cotangent of pi over 2? 0. I love it. 0 plus, and what's cotangent pi over 4?
0.
No.
1.
Yes.
1.
Cotangent is ratio sign and cosine sine, and pi over 4 is where those are equal. So tangent and cotangent agree there. So I get 1. That's kind of nifty. The area under cosecant squared from pi over 4 to pi over 2 is 1. If you had to guess before we got into this section, you would never guess it's 1. Seems too nice for freaky ass trig functions. But oh well, they behave nice sometimes. All right. I think that's enough. Let me get you started on this. This is not a quiz. This is nothing. I would love it if you'd work together. A whole bunch of integrals and stuff to do.
Yeah, I'm a job club. Job, I think, for waffles.